Well, that,
every company you've seen, of course.
well, after the workout, when I do all the,
Yeah.
I was even asking, how come most of the gyms, they all do the same exercise?
Yeah.
Like, literally,
What?
no, that's right.
Yeah.
And like, so you don't check it.
Yeah.
I'm a little like,
Squats.
or if you like 10 minutes without which is, I think, really interesting. Think about this in a practical term.
It's a pretty good way to convince some of the
But I'm
tribes
not
whether or not.
minutes every day, because I have my dog.
Definitely a hard
And then I walk a foot. I do that.
Is, I think 9 o'clock is roughly from her.
Okay.
So I felt like that, but you can do it in the morning, which I'm sad I'm not with her, but yeah.
Oh yeah, we're
Oh, do you have time to?
yeah, totally. I'm sorry, we were trying to figure out what that time was going to be. So no, I'm meeting with
Kate.
Sorry.
10:30
and
to 11.
And then you want lunch?
Sure.
Okay.
You know, take it to lunch. Actually, he's good at steak.
Like with glasses. All right.
Daniel, do you want some water?
No, coffee will be fine.
We'll give people like another 2 minutes, people including me, to get coffee.
Yeah, for sure. Kate, where'd you do your PhD?
University.
Okay.
It's done.
Who'd you work with?
Philippa Clark.
Okay.
She was my chair.
Okay, cool.
I was in, CSET, Center for Social Epidemiology.
Okay. So, therefore, you will be the dean of the School of Public Health someday soon. That's what I'm led to believe about the social epidemiologists in Michigan.
It's the track record. I know.
How? Either that or governor. Like, I don't know. Right?
I know. It's the speaker for the School of Public Health commencement series, Abdul.
Right, sure.
Yeah.
Right.
Yeah. I
And
know.
he's like the least accomplished of
I
that
know.
crew, right?
And there's so
Yeah, but between Hanagia Drew and Sandro and Abdul, it's a little bit like,
I know.
there was something in the water
Nothing at
at
all.
that
At that
moment.
time.
It's been
Actually, on that note, the woman on like but she's
Yeah,
the
I think that was,
pediatrician
after you-
who worked at a University of Michigan.
Oh, wow.
Like
Oh, wow.
Jesus.
Yeah.
Also a graduate of the program.
Sure. Sure, of course. Do you know Jenna first? I saw Jenna and her partner Anthony visited Scarborough like 4 days ago.
I heard because do you know Grace Knopper? She just joined. She's at Student Board. She's now
Oh, cool. Great. Great. Well, right, Allison was there too. Speaking
Exactly.
of like power hitters.
Yep.
Good Lord.
I know.
But no. Yeah. So anyway, Jenna, I walked. You know Jenna's birthday walk thing.
Yes, I
Yeah.
do. The annual tradition.
So I walked like 1.5 miles of her 31 miles this year. She walked the number of miles that she is years old every year.
My husband to do that as a run.
Yeah. Well, this year she did like run half a mile, walk half a mile for the entire 31 miles.
That's awesome.
And finished all in or something with braces. Yeah, it was intense. We like walked through the woods for like 1.5 miles, and I was like,
Half an hour.
It was Monday. It was Monday actually. This week when I did it. Yeah, I was like, I have to prepare for a lecture.
Entire workday, so
It was her entire workday.
Yeah.
So there's also just kind of her work. So it checks out.
That's right. She's like working and doing research at the same time.
This is we have code we want to share with people, and we don't think we have everybody's email address. If you did not RSVP, we don't have your email address, so we can't share it with you efficiently. And we would like to share it with you if you might appreciate it. So if you want us to send it to you, if you just come up and write your name over there, I'll kind of like be in the back sending emails out to people. So if you didn't RSVP, this is not meant to be like, it's totally, we're glad you're here. The RSVP is just so we can get the right amount of coffee and circulate materials to people. But if you would like to receive the email with the code, just write your email up there. I can't think of an easier way to do it.
Yeah, and it's fast. I apologize. I know that's like not ideal for everyone.
It's well documented. I just looked at it.
Okay, yeah, it is well documented, and it's really about the pseudocode more than it's about the code.
If we RSVP, should we have already received it?
No, but you will.
Oh, okay.
There's a good chance you will.
Okay.
Do they need it at the beginning? Is it
No,
like-
no,
okay.
there's like, yeah, I'm going to talk for a while, and then we'll get to the code.
Okay, all right. So, good morning. Thank you for joining us. This is a kind of like gift of an EpiTools workshop because we have Dr. Daniel Westreich, who's an associate professor at the University of North Carolina, here visiting, and partly he's visiting for NIGA because he's on the NIGA Promoter's PhD committee, and never to leave an opportunity untaken. Last time Daniel was here, he gave a terrific workshop, and so we asked him, since he was visiting, if he would come and talk about tools for generalizability. And really, most of Daniel's work has been on HIV and on implementation science, but he's really, I think, in a lot of ways changed how we talk about generalizability and transportability tools, and has written some of the most accessible, some of which I disagree with, but influential and really thoughtful and useful work on challenges of transportability and how we think about this problem in epidemiology. So I am so happy that you could join us, and leave it at that.
Thank you so much, Maria. And we do disagree on a couple of things, which is like what I enjoy so much about coming here, is that you are have great counter arguments to many of the things that I think are true.
Last time you were here and we argued, you completely won. Like
I don't think that's true. I don't think that's true.
It's just like, good point.
Yeah, but that's happened in the other direction. That phone conversation we had when I was, for some reason, in New Orleans, and yet we were talking on the phone.
Yes.
Do you remember that? Yeah, anyway. All right, so, hi, everyone. So I have not given this workshop before, and I've not given it as a workshop with code.
We can wear a mic.
Oh, yeah, absolutely. The mic is... Why don't I just stand here instead?
To hold you back.
It's all right. I can gesture from here.
Sometimes it's in here and it's really not, it's not even a big deal. It's
Okay.
just.
Hello? Yeah, it's on.
Yeah, it's on.
Yep. Great. It was one of those times I wish that the pockets of this vest were actual pockets instead of they just looked like pockets. Right. Okay. This working? Everyone can. Okay. All right. Good. Now I can wander and gesture elaborately. So, and I'll probably use the board at some point. But so I haven't given this workshop before, so I don't know exactly how the timing is going to work, and I don't know if I got the right balance of sort of code versus lecture. But the organization today is that I want to talk for a while about the motivation, because I think behind this stuff, because if you haven't seen me talk on this subject or someone else talk on a very similar subject before, some of this may be weird and hard to get your head around, and why are we even talking about this? And then I'm going to take you through the code. I'll introduce the data. After I introduce the data, I'm going to go back to lecture slides and introduce some of the methods for dealing with external validity and generalizability in theory and in concept. And then I'll bring you back to the code and go through some of the code for actually how to implement these things in a simple setting in simulated data. And then a couple of quick closing thoughts. And I think this will time about right, especially how, given my propensity to sort of spin off a little bit. But also feel free to interrupt me if you have questions. The whole point here is for us all to learn, and at the same time for me to learn how best to present some of these statistical methods and code. So thank you for your indulgence if this doesn't go quite as smoothly as some other EpiTools workshops. So I want to talk through motivation first. And to think through our motivation for this problem space of external validity and generalizability, I want to think about pre-exposure prophylaxis for HIV, a subject near and dear to the hearts of many people in this room. And think about it. So pre-exposure prophylaxis for HIV is this idea that, you know, if people are at extremely high risk of being exposed to HIV, we can give them antiretroviral drugs. And if they take those drugs, then when they are exposed to HIV, the drugs in their system will prevent them from actually being infected with HIV. And so if we wanted to understand whether this worked, and we have a pretty good sense of that at this point, but if it were 10 years ago and we wanted to understand how this works, how would we go about learning about that problem? And often the thing we do in a situation like this is that we will do a trial if we want to learn. And in this case, the trial might look something like this. We take, you know, some large number of people, randomize them to active pre-exposure prophylaxis, an active antiretroviral drug versus some placebo. We'd blind the participants and the researchers, and then we follow people up for some number of months, and we count the number of cases of HIV. And in fact, this is what actually happened. Here's one such trial. In this particular trial, they randomized 4,747 serodiscordant, HIV serodiscordant couples, which a couple in which one person has HIV and the other doesn't, the idea being stable couples, to 3 arms, 2 active pre-exposure prophylaxis arms, 1 single drug, 1 2-drug arm, and 1 placebo arm. And then they followed people up for 36 months, and they counted the number of incident HIV infections. And the results they got were highly protective, right? Taking these drugs, highly protective against acquiring HIV. Single drug was associated with a hazard ratio of 0.33, dual drug with a hazard ratio of 0.25. And then I'm going to make Pam blush. A couple years later, this very nice paper in AJE. Pam, as part of her dissertation work, essentially did a reanalysis asking broadly, what if everyone had been perfectly adherent to PrEP? And this work took a couple of different approaches, inverse probability weights and principal stratification approaches, and found predictably that if you were more adherent, the drugs were more effective. And so the hazard ratios were further from the null in the protective direction. So this is where our research usually stops, right? As epidemiologists, oftentimes we will do either the observational equivalent of that trial or the trial itself. Maybe we'll do an as-treated analysis, but then we'll mostly just sort of dust our hands and be done, right? And we'll sort of drop into the literature something on the ratio scale, often a hazard ratio, maybe a risk ratio, and just sort of walk away from it and say, that's our part of this gig. And I've done this as well, like many, many times. But I think that if we want to influence policy, we have to do more than that. And in particular, we want to think about public health impact of realistic implementations of the things that we're studying in realistic populations. And so, you know, one thing to think about here is that the intention to treat effect is sometimes called the public health effect. You know, the intention to treat effect in a trial is sometimes referred to as the public health effect. I think not as much now as it was 10 or 15 years ago when I was taught that. But it's still thought of that way by some people. The idea being that, well, not everyone's perfectly adherent in the intention to treat effect. And so we get some of the natural variation. And in, you know, in a clinical setting, all the clinician can do is tell you to take a thing. They can't actually force you to take it. And so for reasons like that, I think people tend to think of it as like a more real-world effect. But I think it's really worth thinking through, and I actually am working on this paper now, exactly how an intention to treat effect relates to the effect of the scale-up of a real public health intervention in a real-world setting, right? And like, what are actually the steps you have to take to interpret the intention to treat effect as that public health effect? Those steps, I think, are really worth thinking through. But more broadly, like sort of skimming over the technical details for a moment, I think there are two really broad steps in interpreting the intention to treat effect as some measure of public health impact. And the first is to think about the question of internal validity versus external validity, which is really the focus of most of the lecture today and the workshop. And the second is to think about the difference between exposures and population interventions. And so really briefly, right, I'm going to touch on both of these very quickly just to give you a very, like, here's where we're trying to fit in, and then we're going to focus in on this first one further. But so, like, super high level, a trial or a well-conducted observational study typically is going to identify an internally valid sample average causal effect in your study sample, the average causal effect. And that's the thing that's sort of the target parameter for most analyses, and most of our default statistical methods is to get something like that. But we're really rarely interested in the study sample for its own sake, and it's also extremely rare that we formally identify the target population. It's really notable how you can go to studies like randomized trials which are explicitly intended to identify causal effects, and even the most sort of anti-causal inference grumpy person is going to acknowledge, like, yeah, but the trial will give you causal effects, right? But if you go to literature, like if you go to the Maldonado and Greenland IJE 2002 paper about identifying causal effects, which is really, like, in my opinion, quite entertaining for a scientific paper, Socratic dialogue about, like, okay, but what do you mean causal effect in a sort of, and it becomes one of the things that emerges from that is that no causal effect is identified without a target population. And these very explicit causal studies, like randomized trials, never actually tell you who the causal population is explicitly. And that's like an interesting disjoint that's part of where I'm going to, like, stick the lever in and start prying in a couple slides. And it's important because if the target population differs systematically from the study sample, the average causal effect estimated in the study sample is not going to be the same thing as you would see in the target population, right? And this is literally just a matter of weighted averages, right? If the intervention is more effective in women than men, and our study oversampled men compared to a target population, which, sidebar, many randomized trials oversample men and undersample women, then the average causal effect in the study is not going to be equal to the average causal effect from the target. Right, just simple weighted averages. And that's easy to deal with if it's women and men. It's a lot harder to deal with if it's not women and men, but it's some obscure SNP that you haven't measured, right? And then exposures and interventions, you know, in that trial, the average causal effect was a comparison of risks, asking, you know, what if all people got active PrEP versus what if all the people had gotten placebo? But that's not actually what you care about if you want to change the world, because in the real world, no one's getting placebo. So you're already making the wrong comparison, right? And like, it might be a fine comparison to make. It might be very informative about the real world, but you have to explicitly make an assumption that placebo versus nothing at all are equivalent conditions, right? But then also, you know, uptake is not going to be 100%. Assignment is not going to be 100%. And then there are a whole bunch of other issues that come up in this exposures versus intervention difference. And so we laid out this framework a couple of years ago in an editorial in AJPH for sort of a framework thinking about what we're calling the causal impact framework, where you think about internal validity and then external validity and then the intervention of a realistic, the application of a realistic public health intervention. And so ultimately what I'm hoping is that this workshop will expand. Right now, this is the workshop for point 1, and ultimately I would like a workshop that goes another hour and a half and deals with point 2.
Anytime.
Right, great. I mean, hopefully next fall, maybe. So for the remainder of this talk then, I'm really going to just talk about external validity. And so, you know, very little formal quantitative attention was paid to external validity until maybe 10 years ago. There were a couple of papers. Miguel had a paper in 2008. Frangakis had an editorial in Clinical Trials in 2009. And Frangakis is a trialist and a biostatistician. So the statement that RCT results are useful only if we can calibrate the results to predict treatment efficacy in the target population of interest. That is a very strong statement. In fact, it's stronger than I think. Like, I don't agree with that only, but the fact that in the journal Clinical Trials, a biostatistician used that word only is really remarkable to me. In 2010, Steve Cole and Liz Stewart had I think, what I think is the first quantitative methods paper on this subject. There may have been other ones, but this is sort of, I think within epi is really an inflection point in these methods, presenting inverse probability weights to standardize clinical trial results to an external target population. And this is going to be the first method that I'm going to show you in code later on. Judea Pearl and Elias Barenboim and some others have presented several papers presenting causal diagram-based and causal diagram-adjacent methods for identification of externally valid causal effects. And then there's this other really strong statement by statisticians in a stat journal in 2016 saying the central issue is whether conditional effects in the sample may be transported to desired target populations. Statisticians, epidemiologists, and survey researchers should work together to increase understanding of these challenges. Again, that's a fairly strong statement, I think, for a stat journal from statisticians. The other thing to call out about this quote is survey researchers, because really what these methods are is just survey sampling weights, right? That's really like, all inverse probability weights are in some sense descended from survey sampling weights in the first place. But here it's even more clear. You know, if I want to make inference about the whole state of California and I'm doing a randomized trial of 1,000 Californians, it's pretty clear that if I can identify how to weight those 1,000 Californians back to the whole state, then I'm going to be in good shape. And just so, you know, for another simple example, suppose in a randomized trial we saw the causal effect of the outcome, treatment on the outcome is a risk difference of 10% in HIV-negative women and 20% in HIV-positive women, which is in fact approximately the causal effect, the estimated causal effect of smoking on miscarriage in those populations. There's like a massive difference in risk differences in the effect of smoking on miscarriage. And suppose our study is 50% HIV positive because we oversampled HIV positive women, because we were interested in that difference in the HIV effect. If our target population is only 10% HIV positive women, or it's 50%, or it's 100%, it's pretty clear that the overall causal effect is going to be not the same in all those populations. That's a very simple weighted averaging question. And again, just like with if it were, you know, if this were some other very obvious difference that you would want to do subgroup analysis on anyway, this is not going to be a problem, right, when you do your trial, generally speaking. But it doesn't have to be something as obvious as HIV status. It could be something less obvious, or it could be a combination of multiple factors, right? It could be 10 variables that differ between the two, each of which has a little bit of a subtle effect. So again, the larger problem here is of target populations. Maldonado and Greenland, again, say that no causal effect is defined without a target population. And so, but again, you know, trials and observational studies never explicitly identify their target population. I don't want to say absolutely never, but almost never. And they certainly, I have never seen somebody identify their target population explicitly with great detail, like show me the table 1 of your target population. And so I think it's worth thinking about, like, what's implied? You know, in that Baton et al. Study, which is an excellent study, very well done clinical trial, you know, New England Journal published, checks all the boxes. What is the implied target population? Sorry? So the study sample is the target population is one argument. Yeah, and I think that is one of the things that is often implied. Any other ideas from, yeah, Matt?
What would you, turning the question back at you a little bit, what would you suggest here? I read a lot of observational studies, and there's always the paragraph in the methods, like we recruited from bars, hotspots, looking for female sex workers, and then there's the consort diagram of like, you know, we screened 5,000 women, and these were excluded for these reasons. We enrolled 3,000, etc.
Yeah.
So how might you add more details to make it more worthwhile to this problem?
I mean, the details that I want in every study are the table 1 of your target population. Understanding that that's not realistic in all cases, but that's enough detail for me, right? And that explain to me exactly who your target population is and how your study sample relates to them, if at all.
You
right?
want table 1 of the target population.
I think so. I mean, I'm open to arguments on this because a lot of this work is new, but
We won't be publishing much.
I'm okay if we publish less, but it is more useful. Like, let's not take the diversion into the like labor economy of academic publishing, because that's like its own PhD.
Well, I mean, of course, by that you're meaning that, of course, we've got our hands around it, and it's been enumerated.
So there's a couple issues here, right? One is that almost any study you do has multiple possible target populations, right? You run this trial, for example, this PrEP trial. You could want to apply that in a United States target population or in a sub-Saharan African target population, depending on who you were and why you were reading it. And you could at most really include one of those target populations in your study. But it is probably true that if you're asking for $5 million to run a randomized trial, you have some sense of what you want to do with that information once you have it. If you can't articulate to NIH, here is the policy that I would like to follow from this $5 million trial. Here is the population in which I want to make decisions based on the information I get from this trial. I'm not 100% sure you should get that $5 million. I don't think that's too high a bar to ask people to clear before they do massive studies. And I'll explain more. And in fact, there is an ethical obligation to do so. And I'm going to get to that in a slide or two. But back to this, I think that the other things that are often implied when you do a randomized trial, if you haven't explicitly identified the target population, is that it's either the study sample itself, it is table 1 times 1,000, right? It is the population for which your table 1 in this study is a simple random sample, or it's defined by inclusion and exclusion criteria, right? Like, it's the people who would have shown up in this study according to my inclusion and exclusion criteria.
I think another assumption that goes into, especially some of the trials that are more, PrEP is maybe this, but like a vaccine trial for sure.
Yeah.
Is the assumption that if you, and this works with PrEP actually, so the assumption that if you know adherence, you know the outcome, and that, that there's some part of that mechanism that is constant across all people, and we're just going to informally understand that, but not actually be very explicit about it. And so then which, I don't think is right, but I think that there's some of that thinking about, like, if we're doing a trial of some intervention that should work for everybody, then it doesn't matter who we include, because what we learn is going to be applicable for everybody.
Yeah, so I think we're like getting into this territory about like how much we're biologists here and how much our trials are actually getting at biological findings rather than epidemiological findings. And there's like a big culture split, I think, within epidemiology. If you, Ken Rothman had a paper 5 years ago now called Why Representativeness Should Be Avoided. Wasn't that the title? And what was so notable to me about that paper, and I don't know if you've read that paper, I think people have probably heard of it. I feel like it got some mind share. But if you go to that paper and you go to the very end of that paper, he has this statement at the end that says, the goal of biological research is to establish truth, like truth for the human, like for humans or something like that. And I just find that so remarkable because he thinks we're doing biological research. Like that's what that sentence tells me. And I don't think that's what we're doing. I think we're doing epidemiological research, and that biological research is a somewhat different department. And not that there's no overlap, but that I expect there to be more heterogeneity than that. The other thing to note, even with things like that have a biological truth to, like let's say for the sake of argument that yes, PrEP works exactly the same or sufficiently exactly the same across all people, across all levels of pharmacokinetics and liver enzymes and like all, whether or not you ate Brussels sprouts or grapefruit today, like all of the things, right? It's still the case, and I'll get to this in a couple slides, that you're always going to have effect measure modification on at least one scale if you have non-null causal effects, and any other causes of the outcome, right? And some of you, like, we may know that, we maybe learned that, but the implications for generalizability are really strong. It might be that the risk ratios are the same across all of your populations, but as soon as your baseline risks start to change, then if your risk ratio is constant, your risk differences have to change, and vice versa, right? That's just the math of it. So even in that case, I'm not...
Yeah, I think it's more of like if you think that this intervention reduces your risk to 0
Yeah.
for everybody,
Right.
who cares how you count it? You're
Yeah.
reducing the risk to 0.
Yeah, for sure.
It's not like, it is clearly not correct, and especially not like precisely correct.
Yeah.
So then is the implication that we should just always assume that there's going to be tons of effect modification everywhere all the time in all the places, and that's one of the reasons why this matters so much, is because there's never going to be a case where there isn't that effect modification.
I think there are plenty of cases where there isn't that effect modification. I just think that you shouldn't assume that there's none. And I think to date we've all been assuming that there's none.
Is there any work that tries to like get a handle on that?
You know,
How
so
often,
there's
what context is
no.
The Harvard people have said that they've counted up
Oh,
thousands of
boy.
studies that have never seen a case of, there's one, Walter Willis.
Yeah.
Multiplicative
Yeah.
actions. You do have to be careful about what
But
scale.
is that what they're
Actually,
saying, or are there studies on
well, I'd love to hear Dan's
Yeah.
Dan's thinking.
No, I mean that's all. So there's lots of anecdata, right? But even that anecdata, like the Harvard, right? There are claims like from Donna Spiegelman and Walt Willett that like we in my 600 papers, my 500 papers, I've only ever seen 4 times when there was statistically significant multiplicative scale interaction. But like even just by like multiple comparisons reasons, you should have seen a lot more than that, right?
Yeah.
Like if you're checking 2 variables in each of 500 studies, that's 1,000 variables. Yeah, you can do the math on how many you should have seen, right? Because nobody's doing Bonferroni over their 500 studies, right?
And isn't that just proof too that there is interaction on the additive scale for all of them?
And that too, right? Like they're not checking both scales. And like, whatever, there's not that much power. The other thing is that there's not much power often to detect interactions. And so these things, like things that are mathematically true may not be statistically true in your study because actually you've split the data 4 ways and like you no longer have the right power. Like you no longer have sufficient power to find it. But I don't believe the anecdata because it doesn't actually line up with, I mean, unless like these are totally non-normal distributions, which nobody is yet arguing. Like I'm not convinced by that. And I've asked some of the Harvard folk that and have not gotten an answer yet, so I don't know.
I think that assumption of constant effects is less tenable for like social exposures than like maybe for like a vaccine or something too, because for social exposures, like people experience the world differently. So like I study education policies. Like,
Yeah.
for exposure like that, you wouldn't expect a white man and a black woman to have the same.
Yeah, well, it's interesting you bring that up because one of the conversations that Maria and I have had about this was how often can effect measure modification reverse effects? Like, we feel pretty confident that confounding can reverse signs, but often I think we feel like effect measure modification it's going to change the magnitude, but it's mostly going to stay on the same side of the null. But exactly like privilege, anything that's intersectionally about privilege is a place where you can reverse sign.
Sorry, just that disagreement, isn't it really like if there's mechanistic interaction, like if there's truly like... I feel like there's...
Maybe. Well, let's talk about that more later. But like, we know exactly that like there's all sorts of research that that like assertiveness is perceived in the workplace is perceived very differently by what your gender presentation is. Right, and it can be like very positive for certain gender presentations, very negative for other gender presentations, and like that's a place where there's effect measure modification. You can think about that as effect measure modification by gender presentation or sex, depending on what terms you're using, that reverses sign of some intervention, right? And I do think that those sign reversals are more likely to happen in social contexts than in like more biological contexts. But I also think that this is like a continuum, and that there aren't any hard cutoffs in there. So these are sort of the three things that I think are implied in terms of target populations that I went over before, but I don't actually believe that any of these are really people's real target populations when they imply them by not actually telling you who their target population is. Sometimes these are true if you have a very large-scale pragmatic trial. I'm not really talking about, randomizing 320,000 people or whatever Maya Peterson is doing right now in Africa. Like, it's not like a gigantic pragmatic trial where you have basically no inclusion and exclusion criteria in the first place. You're just like trying to change a community. But in a smaller, traditionally randomized trial, inclusion and exclusion criteria often reflect risk enrichment. We often deliberately oversample high-risk people, specifically so that we can power our trial better. In that PrEP trial, you may or may not have noticed, it was conducted among serodiscordant couples. Serodiscordant couples, the HIV-negative person in a serodiscordant couple is guaranteed to be exposed to HIV. There are other things that are often strange about serodiscordant couples, and we could talk about those. But if you think about your causal types, the doomed and the immune and the protected and the harmed, in selecting serodiscordant couples, you have removed from your study sample a whole class of immune people. The type of immune people who are immune, like who it doesn't matter whether they get PrEP or not, they're never going to get HIV because they're never going to encounter HIV, right? They never get that necessary, like that component of their sufficient component cause or whatever, because they never come in contact with HIV. None of them are in your study, right? So you have this non-generalizability potential already that's defined by your inclusion and exclusion criteria.
The quickly doomed are out as well.
Possibly, yeah, depending on how you, on exactly what your inclusion and exclusion criteria are.
Question about that last point.
Yeah.
If someone is not exposed, isn't that a positivity violation? So you would want to exclude them?
You might, but in effect you can't, right? Like, yeah, out in the world, I don't, that's a good question. The thing is, like, well, no, because it's, the problem is that the word exposure is being used in a couple different, it's overloaded, right? The exposure in that trial was PrEP, right? And this is a randomized trial. Everyone in the trial could get PrEP or not get PrEP, right? So there's no positivity violation on the exposure that we're randomizing. You can't get the outcome without this other thing happening. There's a mechanistic interaction between PrEP, PrEP or not PrEP and a bunch of other things, and exposure to HIV before you can even be infected, right? So you can't ever get the outcome in that case. And like, but there are lots of people out in the world who will never get the outcome, who are never exposed to HIV, right? That's actually who you want to give PrEP to, includes a bunch of people who will never ever be exposed to HIV, right? Those people are out there because people don't know, like the whole point of the PrEP is that maybe you're not going to discuss or test before you have sex or can't for whatever reason. And so, but so you don't know, right? And we don't know if everyone's going to be exposed or not to the HIV. Does that make sense? All right. I'm not sure that was the clearest explanation, but so inclusion and exclusion criteria, the superpopulation for table 1. So first of all, we rarely want to generalize only to those people who, had we approached them, would have consented to be in our trial, right? Agreeing to be in a trial reflects a bunch of other social factors that we may or may not want to select on, in addition to all the things I said on the last slide. For example, trials often wind up recruiting people with greater health-seeking behaviors. Like in the PrEP trial, it may be that you recruit people who are more likely to use condoms, right? And the people who want to be in the trial are exactly the people who take more steps to prevent themselves from getting HIV from their infected partner in ways that have nothing to do with PrEP. And what about the study sample itself? Which I think people do believe. And so the first problem with that is sort of a technical, nitpicky one, which is time. Even if you only care about this population, it ages over the course of studying that population, and time has passed, and other things maybe in the background have changed. And so it's not exact, even in like the largest pragmatic trial, the people you want to apply your results to are a little bit different than the people you started studying. That's probably not a big deal in most cases. Like if it takes you 3 years, and yeah, everyone's a little bit older, but it's not like you waited 30 years. But the other thing about the study sample itself is an ethical issue. And so I took this actually from UCSF. DHHS regulations define research, this is from your IRB, as a systematic investigation, including research development, testing, and evaluation designed to develop or contribute to generalizable knowledge. What is generalizable knowledge? Information based on results or findings that are expected to be reproducible and applied broadly with the expectation of predictable outcomes. Right? And applied broadly to me says very clearly outside of your study sample. And so if you agree with me with that interpretation, then when you get IRB approval, you are promising them that your study sample is not your target population. Like you are committing to that. And like it is an ethical obligation that they're not the same thing. Right? Which is interesting. And like sidebar, this is one of those places where methodological decisions you make, like who is my target population or have I identified my target population, encode ethical values. Right? The other place where methodological decisions encode ethical values is often is in diagnostic testing, where a lot of the things people do in diagnostic testing is to sort of treat sensitivity and specificity as basically equal measures. But the ethical issue that encodes is a particular weighting of false positives and false negatives. Right? If you don't explicitly weight how bad a false positive is and a false negative is while you're thinking about sensitivity and specificity, and in the worst case, if you're just like, I don't know, take the sum of specificity and sensitivity and like whatever's best in the sum, like you're making all sorts of weird implicit ethical judgments that like might be fine, but you're sure making ethical judgments there about how bad the false positive would be versus how bad the false negative would be. And I think as epidemiologists, we don't think quite hard enough about what ethical judgments we're incidentally making in our methodological decisions. And this is one of those. So there are these two different kinds of external validity, which are going to come up later. When the study sample is a subset of the target population, this is generally called generalizability. Other cases are usually called transportability. I don't think that these are radically different things. Pearl and Barenboim seem to think that they're more radically different things than I think they are. And in general, I don't think Judea is wrong about things. He's very smart. But this is a place where I don't agree, and my disagreement may just be because I do not understand. But later, I'm going to show you the code and the method to deal with generalizability, inverse probability of sampling weights, and transportability, inverse odds of sampling weights. And I'll show you that difference when I get to the code, which will maybe be in 5 to 10 minutes.
Sure. Would you settle for, you talked about the three.
Yeah.
Here we like to teach, indeed, in any causal or in any task, a statement of the target population before, right at the beginning of one's method section. Would you settle for a 2 or 3 sentence narrative explanation? We've never got table 1.
Totally. I will settle for anything better than what we're doing. Like I'm not going to solve this. We're not going to solve this. What we're going to do is what I want to do is, assuming I'm right, is make all of our research a little bit better, right? And being explicit, I am hoping these results will apply to all U.S. residents between the ages of 35 and 55 who X and Y and Z. Even that is much better than what we've got, which is that's left implied, and I'm not totally sure what you think it is, and so then we may have very different ideas, right? I do think, though, that it wouldn't be that hard some of the time if you were doing a randomized trial, and you were doing it very intentionally, especially if it's a big, expensive randomized trial, to build in, a very small survey in your, identify your target population and then do a very small, 2,000 person survey of your table 1 information. The stuff that you suspect could be strong effect measure modifiers that could be imbalanced between your study sample and your target population. And it would make the trial slightly harder to do in various ways. But I don't think it's that much effort compared to the effort of putting together a 3,000 person 5-year-long trial to send a couple people out into a community or call some people on the phone. And that's the kind of, I think, small incremental effort that could then give you much richer information on who your target population is and allow you to quantitatively evaluate, is there a difference between the people I actually enrolled and the people I really want to represent on these important characteristics, say age, self-reported race, self-reported sex, and a couple other things that we think might be important given our substantive area. That may be too much. That may be too much to ask. It's hard enough to do research, but
That's impossible. That's another grant in its own right. You're talking for prep in this city. It was really geared towards gay men. There's been a single random sample done in 1985 as part of the maths by Warren Winkelstein, an epidemiologist, who even there, that was door to door with only 60% response. It just, you'd have to agree, that's asking for a lot.
It might be asking for too much. It might be. Meg, what were you going to say, though?
I mean, I think that getting a truly random sample of the target population is probably really hard, but what probably isn't as hard is at least giving some information about the people who you screened but didn't end up enrolled. Because you have information about those people, and you consent people before they take this, whatever your screening survey is. I mean, we did this in IBREX, and the data were not published, and that's irritating. And so, like, that information's there, and just knowing the difference between who you enrolled and who you tried to enroll is informative.
Yeah, and that is not uncommon. Yeah. So I know that the ECHO trial of hormonal contraception and HIV outcomes has that information, right? They've got, I think they screen 12,000 people to enroll 8,000 or something like that. And they know who the 4,000 people are, and they know what they look like, and they know, and so at some point in the future, we could check, are they systematically different from the people who actually wound up enrolled? You may be right. Like, it may just be too hard. But there are other sources, is the other thing, right? There are things like the DHS, the Demographic and Health Surveys, which if you were doing a study in South Africa and you wanted to apply your results to the general adult population of South Africa, we have every 5-year demographic and health survey data, including some HIV indicators, right? And like, maybe that's enough. And then you don't have to do a completely different piece of work. You just have to think about where the data could come from and maybe even include it in your study, like in your published work.
I mean, it's certainly all in the right direction. The 2 or 3 narrative sentences about what the investigators intended, I think, goes a long way in focusing the reader, naive and sophisticated, into exactly what you are going to get at.
Yeah.
How is the study sample inference different than what I'm really interested in, which often passes the reader by if you don't put it in her or his face.
Yeah. No, I think that's a great point. And that at least does not take a huge amount of extra effort, right? It takes some thoughtfulness, but it doesn't take another $100,000 to write those 3 sentences. So thinking, one of the ways we can sort of think through how this external validity stuff works is by thinking about generalizability in particular, where you have, I want to know about the state of California, so I do a randomized trial among 1,000 Californians. Because that's really just a missing data problem, right? That's really all that is. It's like we have data on the 1,000 people, we have missing data on everyone else, which is a lot of everyone else. But it's fundamentally a missing data problem, and so we can use causal diagrams in much the same way as we do in missing data problems. So we'd start wanting to understand the effect of pre-exposure prophylaxis on HIV. The first thing we could do, and this gets a little bit to Mega's point, is that we can think about how this drug effect on acquisition of HIV is fully mediated by the levels of the drug in your blood. Like, that's basically how this drug works, is that you get this drug into your blood, and then when you are exposed to HIV, it is in your blood. So the reason to break out that mediator is that now it's easier to draw the role of adherence in here. And what's interesting here is that we have a structural or mechanistic interaction, at least on the margins, because if your adherence is 0, there's no causal effect of PrEP versus placebo. Like if you're not taking the thing, it doesn't matter. But also if you're in the placebo arm of the trial, your adherence doesn't matter, right? And so this is interesting because it gives you modeling leverage. You know, in particular, that in like a regression model that had a beta on PrEP and a beta on adherence and some beta for their interaction, all of your causal effect should be in the interaction, right? And if you're getting causal effect, like if you're getting estimates of effect on the main effects, something weird's going on, right? Either measurement error or something else. But like structurally, we know that if PrEP is actually, if you're actually getting placebo, there's no causal effect of adherence on your outcome, right? Not directly. And this is a nice example of Koop's axiom from C. Everett Koop, which is drugs don't work in patients who don't take them, which is interesting. It's also false for infectious diseases because your flu vaccine protects me. So then we have this diagram, and then we can imagine, I think, that people who have like a health-seeking cluster of behaviors, aka they floss daily, those people are more likely to be adherent to their drugs. They're also less likely to get HIV for various reasons, right? Not because they floss, but because maybe the people who floss and who are more adherent to their drugs and always finish their course of antibiotics, those are the people who are also more likely to use condoms, say, or not to share needles, or whatever the behavioral pathways are that are not the same. And so if our study is more likely to recruit health-seeking people with health-seeking behaviors, then we could draw this arrow to sampling into our study. And applying the rules of DAGs, what we know is that because there is an open path between S and the outcome, we can expect the results of this study to not be generalizable on every scale, right? And the difference between causal diagrams for generalizability and missing data, like this one, and causal diagrams for confounding, is that, and this is part of Mega's dissertation, everyone should come tomorrow, is that there are cases where, even though this causal diagram tells you there ought to be non-generalizability, you could actually see generalizability because it's a scale-specific phenomenon. You could have no effect measure modification on the ratio scale, and if you're looking on the ratio scale, everything is fine. Right? This causal diagram doesn't tell you what scale things may be operating on. So this causal diagram analysis for missing data gives you sufficient conditions, not necessary conditions. And so to get into that slightly more, okay. So fundamentally, this is just a missing data problem. Rion Daniel has this really nice paper talking about causal diagrams for missing data. Probably a bunch of you have read that paper. I would urge you actually to go back and read it very carefully because it's got some weirdnesses in it that I've only really discovered in the last 6 months. For one thing, what she defines as a causal effect is actually a risk. It's like it's a single sample. A causal effect is a single sample thing for her, and I think often in epidemiologic usage, a causal effect is a contrast in risks. So she's using causal effect in a different way than you might be thinking she's using it. And the other thing is that her claim is that she is about identifying conditional causal effects. But by conditional, she doesn't mean we condition on some things in a regression analysis. What she means is like, in Z equals 1, I can identify the risk among the exposed and the risk among the unexposed. And in Z equals 0, I can identify the risk. Not, I controlled for Z in a regression analysis and averaged over levels of Z. Right? And both of those things are called conditional risks, right? Or conditional effects or whatever. She only means the stratum specific one. And like, it's very subtle in that way. She's not wrong about anything, but it's very easy to, I think, miss those subtleties in that paper. And we've got some ongoing work addressing that. A student, Rachel Ross, is going to be presenting at SER some of these findings. The identifications for generalizability really parallel those for internal validity. So instead of exchangeability, the way we normally think of it for internal validity, we have sort of external exchangeability, which you can think of as no uncontrolled for effect measure modification, or no unaccounted for effect measure modification. And instead of positivity, we have transport positivity, like no empty table cells in the target population with respect to the study sample. So if you have a bunch of 70-year-old women in the target population and no women over age 50 in the study sample, you can't get from one to the other without a lot of model extrapolation, right? You just don't have anybody who's a 65-year-old woman to generalize to, right? And so one useful way to think about all of this then is that the actual gold standard for causal inference for a particular target population is not a randomized trial, but it is a randomized trial in a random sample of the target population, what you could call a doubly randomized trial or a super randomized trial. If you sample from the target population to the study sample, you have exchangeability and expectation because the distribution of your effect measure modifiers will, in expectation, be the same between those two populations. And you'll have positivity because all of your data patterns in the target population will, on average, be represented in the study sample, and so on and so forth. And so Alex Breskin, who is, I guess, technically still my postdoc for 2 more months, but is really like already moved beyond, has some work in press looking at bounds on the risk difference. And it turns out that, so if you're not willing to make exchangeability assumptions, you can't point identify risk differences, right? But you can get bounds on the risk difference without exchangeability assumptions in observational data. And it turns out that the bounds attributable to external exchangeability are wider than the bounds attributable to internal validity. So mathematically, and just in terms of the bounds themselves, when you make the assumption of no uncontrolled confounding, like you just take a crude analysis as a causal effect, say, mathematically that assumption is less strong than if you take a well-estimated causal effect and assume that it applies in an arbitrary target population, assuming you're not willing to make any exchangeability assumptions at all. You're never actually willing to make no exchangeability assumptions, right? You're always willing to make some. You always have some variables. There might always be some uncontrolled confounding or effect measure modification. But if you think about the potential outcomes, in internal validity, you've often identified half of the potential outcomes, right? If you have a dichotomous exposure, dichotomous outcome, you observe one potential outcome for everybody, and there's only one more potential outcome for everybody, so I'm missing half. Externally, you're observing 0 potential outcomes for anybody. I observe nothing about those people who were not in my study, right? So from an imputation standpoint, I have to impute half internally or everything externally. And usually that's just an absolutely larger number of potential outcomes that I have outside of my population, right?
So this is really interesting. Does this then, and this is like also, I think, potentially trying to be irritating. So does this mean that if your goal is target validity,
yeah,
then you're better off doing a simple random sample of your target observational study than a randomized trial, a selected population that is probably not generalizable to your target population?
So I think that's I don't know. We should talk about it. The problem with that is, this gets to the discussion that Maria and I keep having. You gain information doing a randomized trial that you don't gain doing a simple random sample of the target population. In particular, when you do a randomized trial and you come up with a non-null result, in terms of causal types, it tells you definitively that there are people who are either helped or harmed, depending. Right? You definitely have some people of that causal type that exist in the world, which is not information you had before. Right? And that is not a thing you can get. Right? And I don't know exactly how to think about that information, but it's real. It's a real thing. And it is an argument for why maybe we should prefer the randomized trial to start with. because it gives you that piece of information very clearly. But like, this is a much longer discussion, and I've been talking too long, so I'm going to like push on to the code.
Explain this a little bit more.
Sure.
Is the fact that the bounds are due to external exchangeability are wider than those for internal because external invokes both? Like you have to have.
No, sorry.
Really like if you.
Yeah.
If I tell you this is the fact of the internal effect estimate.
Yeah.
And now you go generalize that. You then come back to me and say, now how do I think about how to? What am I comparing the bounds?
Yeah, sorry. So this depends on the definitions of internal and external validity that we advanced in the target validity paper, where we define internal validity as the difference between the truth and the estimate within your study sample. And external validity is defined as disjoint from that, the difference between the truth in the target and the truth in the study sample, right? And so it's not, the external does not include internal, right? They're fully disjoint. I think the most useful way to think about this is how many potential outcomes are unknown, because that's what defines the bounds, right? Internally, the thing that defines the bounds of the risk difference are, well, half of my potential outcomes are unknown. What could they be? If they're all this way, then this is one. If they're all the other way, then this is this other bound. That's what gives you the internal risk difference bounds, is the not assuming that you know anything about the unobserved potential outcomes, because it's exchangeability that lets you assume that you know something about those unseen potential outcomes. And in the external validity, you've observed 0 potential outcomes for anyone, right? Because they're not in your studies. You don't know under either circumstance, which means that the bounds attributable can be, those values can be basically anything. And so they're much wider bounds. In truth, you're always willing to assume you know something about the potential outcomes in the external population. Like, these people look like these people, we're pretty sure that they're going to act, so this is like deep theory, right? This is not going to come up in practice that much. But I think mathematically it's really interesting that there is actually more uncertainty attributable to the generalizability step or the transportability step than to confounding, absent the willingness to make exchangeability assumptions. But this is like its own hour-long talk, so I'm going to leave it. Okay, so I'm just going to skip a bunch of this stuff and skip to talking about the data and some code. So these data, let's see if I can make this a little bit bigger. Okay. And you can open this code using WordPad or something if you just want to look at it. What's important is understanding the pseudocode, not the actually running it in SAS necessarily. So this is a data example taken from Katie Lesko's paper on generalizing study results, potential outcomes perspective. I don't know if I can actually. Is there a, can I do view? No. Sorry, I don't think that I, okay, yeah, thank you. Sorry. So we have here, these data are as Lesko described them in this paper. We have a treatment A, which is a random Bernoulli variable with 50% prevalence. It's a coin flip, right, whether you're A or not. We have 2 variables, W1 and W2, which are at 15% and 20% prevalence. We have our outcome variable, which is a function of A, which is the 1 here and the 1 here, and the 0 here and the 0 here. And here we're calculating the potential outcomes under A1, A equals 1, and A equals 0, right, for each individual, because it's a simulation, so we can actually be explicit about the potential outcomes. And an individual's outcome is this equation. It's 0.1073 minus 0.05 times your value of A, times A, plus 0.2 times W1 for your value of W1, plus 0.2 times W2, minus an interaction between A and W1 and W2. Okay? And then over here, this is py0, and we just have a 0. So the A term drops out, and this interaction term drops out. Right? And then we calculate actual y1 and actual y0 as a Bernoulli against these probabilities. Our effect in an individual is y1 minus y0. Yep. Oh, yeah.
Are you following? Yes? Are you following? If not, please ask for clarification. We will want you to follow this.
Yeah. Okay. Yeah. All right. So, and so this is the actual outcome, right? Which is a random, these are probabilities. This is the actual outcome, and then y is the outcome we actually observe. So if you were actually treated, then we observe your y1, right? And if you were actually not treated, a equals 0, then we observe your y0. So we generate 100,000 observations like this. And I will just run that code. And I will now, this is not actually written in, but I can print out some observations from this data set. And so we have 10 people, numbers 1 through 10, who have, various values for their W1 and W2. And for their A, they have probabilities under Y1 and Y0, which are sometimes, so this is a 5% or 6%, and you draw against that to get your dichotomous outcome of yes or no. And you draw against this to get a dichotomous outcome, and sometimes those are 1 and sometimes they're not. And then we have an effect, which is the difference between these two things, and then we have the y we actually observed. And so, for example, this person has a y equals 1, which corresponds to the y0 because their a is equal to 0. Because their a is equal to 0, we get to see in y their y equals 0, their y0 value, not their y1 value. Does that, everyone follow that? Okay. So now, from here, in the same way that Lesko described, we sample 2,000 people from this data set into our study sample. And we sample them based on their W1 and W2 values. So we sample 320 people who have 0, 0, 480 who have 0, 1, 480 who have 1, 0, and 720 who have 1 and 1 for both of those values. And if you go up there and you see that y1 and y2 are independent, right, at 0.15 and 0.20, respectively, it only should be about 3% of the total population that has W1 and W2 both equal to 1, right? 0.15 times 0.20. But here, we're sampling 720 out of 2,000, or about 36% of our population has W1 equals W2 equals 1. So we're wildly oversampling that group of people, right? And similarly, we're wildly undersampling the both equal to 0 group compared to the original population. And W1 and W2 are both effect modifiers here, right? So we're going to munge things about and create a final data set in which there are the 100,000 people, and in those 100,000 people, 2,000 of them are in our sample, right? So we sampled those 2,000 people, we labeled them all S equals 1, and then we identified them within the larger 100,000 target population group. So this is a case of generalizability, where the study sample is fully within the target population, right? It's fully contained. And you can view this S equals 1 exactly as So the analysis we're about to do, you can think of it in certain ways as a complete case analysis under missing data, right? We're missing 98% of our data. Our study sample, we're going to analyze our study sample, which is just like analyzing complete case. What we want is inference on all 100,000, but we don't get that directly. Okay, so now we're going to do very simple analyses here. Amongst the total 100,000 people, the causal effect, the difference across everybody between y1 and y0 is negative 5.5%. It's about what you'd expect it to be from the simulation code itself. But now if you limit down to only the 2,000 people, the difference, the causal effect is negative 9.2%, which is fairly different than that negative 5.5%. Almost a factor of 2 different. And this is misleading, right? So the question is now, how can we sort of crank that 9.2% back to the negative 5.5%? Right? And so there are 3 main ways that we can do that. The other thing to note is that as I move forward in this code, henceforth we're going to pretend that we don't know the outcomes in the full outcome data set. Right? Like obviously if we did know them, we wouldn't be doing any of this, right? That's all imaginary. All we have is what we observed in the S equals 1 group. Okay? So the first method is inverse probability of sampling weights. This was described by Cole and Stewart in AJE in 2010. And I'm going to conceptually go over it a little bit in these slides. But before I do, this is approximately the data set as it's been simulated, right? We have an A with some causal effect on Y. We have W1 and W2, which both affect Y. And W1 and W2 also affect sampling, right? And these two are independent, right? They interact, but that's not a thing we can show easily on a graph, which is one of the issues with graphs. So there are 3 analytic approaches. First, inverse probability weights, then inverse odds weights, and then the G formula. So conceptually, inverse weights, suppose that we have this population in which, this is our study sample, we have this population in which we have sort of equal amounts of z equals 0 and z equals 1, or W1 and W2, say. And we want to know what would happen if we were in a population in which we had 1,600 z equals 1 and 400 z equals 0, right? So our study sample has oversampled z equals 0 and undersampled z equals 1. And conceptually, you can get from here to here by weighting. These 1,000 people need to represent 400 people. These 1,000 people need to represent 1,600 people. Very simply, the weights here would just be 4 over 10 and 16 over 10, right? And if you apply a weight of 4 over 10 to everyone in this group, you wind up with the equivalent of 400 people. And 16 over 10 in this group, you wind up with 1,600 people. And then you just take the weighted average, right? So that's the concept of the weights, right? Then there are 2, and so the algorithm for these weights differs between the inverse probability weights and the inverse odds weights for reasons that I'll get into in a second. But so in the generalizability case, take the target population where those in my study have S equals 1. Right? So we have 100,000 people, 2,000 of them have S equals 1, the rest have S equals 0. Model the probability S equals 1 given some set of variables Z that we believe are important. In this case, that set is W1, W2. And their interaction, because we know that that's the right model in this case. This gives you probabilities. Use these probabilities to construct inverse probability weights, as in 1 over the probability. And then weight these individuals with S equals 1 so that they stand in for the whole population. Right? And that code is what the next code I'll go over. But this differs from the algorithm for transportability. In transportability, remember, the study sample is not a proper subset of the target. They're separate populations. And so there isn't a neat, like, you're not just weighting them up, right? You're not weighting the study sample up to the target population. You're weighting it over. And the people in the study sample are not members of the target population, right? So they themselves shouldn't get any weights. Like, they themselves don't actually appear in the target population. And that's like, it's a somewhat subtle difference, and it doesn't matter that much when the target population is wildly larger than the study sample. But when they're close to the same size, you can run into problems. So in this case, take the study sample R and the target population T and assume no overlap, right? And you've got to estimate what the weights are to get from over here to over here. And so the way you do that is that you concatenate those two populations. You put R and T together, where the people in R are labeled S equals 1. Then you model S equals 1 given Z, same thing as we did before. Use these probabilities to construct odds rather than use the probabilities themselves. And if I have time, I'll show you exactly why that is, but I'm running short on time. And then weight using the inverse of these odds. But the thing you essentially want to do is weight S equals 1 so that these individuals stand in for S equals 0 only, and this is like the effect of the treatment in the untreated. Right? Because you have the treated, who are S equals 1, and you have the untreated, who are S equals 0. And you want to know, what if S equals 0 had been S equals 1? And that's like asking the question of, what's the effect of the treatment in only the people who weren't treated? Right? Yeah?
We have really struggled with this issue.
Yeah.
In the case, and I'm going to tell you the case,
Yeah.
which is we have a special study population, which is some weird convenient sample of Californians.
Yeah.
We're weighting to Californians.
Right.
Using a randomly selected representative population sample of Californians. So this population is not, like, these people are not in this,
Yeah.
but they're in the concept.
Yeah.
You know what I mean?
Yeah, I would treat that case like this.
It's an odds.
I would treat it like an odds.
So otherwise your survey weighting is going to be wrong because it won't incorporate, like the people in your study population won't have like a survey weight, right? Because you're using chips.
Yeah.
Yeah.
So like they won't have a chip weight.
The reason for the odds is really about the concatenation more than it is anything else, right? And so if we go back to this slide, so say that these are our two populations, right? Good thing I'm wearing this microphone. We have the 1,000 people here and the 1,000 people here, and we have the 400 people here and the 1,600 people here. Say that these are actually our two populations, right? This is Z equals 1. If these are completely separate populations, which sounds like the case you have, you concatenate them together, right? Now we have 1,400 and 2,600 people. And you ask, and this is S equals 1, this is S equals 0, right? And you ask, among these 1,400 people, what's the given Z equals 1, what's the probability? Right? What's the probability of S equals 1 given Z equals 1 in this population? Right? What is that probability? Probability S equals 1 given Z equals 1 equals, right? Everyone agree with that? I didn't get that wrong, did I? Okay. And the probability of S equals 1 given Z equals 0 is 1,000 over 1,400, right? Those are your probabilities. Calculate the inverse probability weights and apply them to these people. Okay, well, the inverse probability weight of this is, okay, so we would do 1,400 over 1,000, and we would get 1,400, which is what we would expect to get, right? Right? And so when you do this, you wind up representing this population, which is not the population you want it to represent. You want it to represent only this population, right? That's what you were trying to represent with these weights, is only these people, not all of the people together, exactly because S equals 1 is not part of S equals 0, right? If, on the other hand, you say, okay, well, this is the probability, what's the odds? Right, well, the simple way is just to, like, do this, right? right? Those are the odds in those cases. It's just probability over 1 minus probability. If you invert this and apply it here, you get that. And if you invert that, 1,600 over 1,000, you get 1,600. So when you flip it to the odds, what you are doing is taking these people out of the denominator. Or sorry, taking these people back out of the denominator. Right? When you concatenate them together and calculate a probability, these people wind up in the denominator. You actually want them out of the denominator if you want to represent this population itself. Right? So once you concatenate your two populations because they're distinct, you have to undo that by calculating the odds instead of the probability. Right? The odds is just a trick in that sense for getting those people back out of the denominator where they inadvertently wound up. I know that's not 100% clear to everybody, but it's not so much about the transportability question as it is about the need to concatenate two distinct data sets.
It's more, is it correct to say it's more about like where your data actually come from rather than the conceptual idea of transporting to like study in San Francisco, transport to chess versus,
Yeah, I think so. I think it's about like what your data structures are like and how you need to manipulate them.
Sub-study within a parent trial is going to be a general.
I think so, yeah. A sub-study within a parent trial is definitely a missing data generalizability problem. But if that sub-study came, you weren't sure what the overlaps were, and they were totally distinct data sets that you needed to concatenate, then you would have this kind of a problem. That kind of distortion is key there because the data sets are similar size. So the trick that Cole and Stewart proposed in 2010, the other thing you could do instead of calculating the odds weights here is to multiply this by 100,000. If you multiply this by 100,000, the proportions stay right, but the influence of this in the denominator is tiny, right? The reason that the odds and the risk differ here is exactly because it's a probability over 10%, right? So now we're back to like second day of epidemiology 101. Okay, and then the final approach conceptually is the G formula, aka parametric G computation. And here, this is actually an incredibly simple way to do generalizability. And conceptually, all you need to do is model the outcome within your sample, sort of obtain a model, like beta coefficients from a model, and then feed the target population through the fit model, right? One person at a time. Apply those beta coefficients to predict outcomes in the target population under relevant exposures. And you can do this all in one step by using John Snowden's trick within SAS. I don't know if this works equivalently in R, but I'll show you that in the code now. Okay, so the first of these methods, again, is inverse probability of sampling weights. And so all we're doing here is fitting a generalized linear model for S, right, which is sampling or selection, based on W1, W2, and W1 times W2. And we're outputting those probabilities into this data set. We're calculating inverse probability of selection weights as 1 over those probabilities. And then we're going to check it and print it out. And so I'll just run that code. You can see that it actually prints out probabilities of selection, where the probability of selection varies based on what your W1 and W2 are.
That model was run in the entire population?
That model was run in the entire population.
Okay.
That's right.
But you would never actually.
So there are circumstances under which you would, like, sorry, go ahead.
No, that was the question.
Yeah, no, I think that I think more likely than not, you will not have the full population. But this is not any different than if you had like a validation sub-study within a larger population, right? This is exactly the same. Right. All of the, and like this is also not any different than inverse probability of missingness weights. Right.
You don't have the outcome measured.
You just don't have the outcome measured in the other 98,000 people.
But you have information on W1 and W2.
Yeah.
Yeah.
Yeah. Yeah. And in fact, you might have that depending on how you had the state of California data. Like if you had the full census data for the state of California, you could argue that you have all of that, right? then it depends, like, can you identify who your S equals 1 is within that larger data set? I think more often than not, it's the next thing you're going to do, which is that they're distinct data sets that you concatenate together. But I think this is an important method, and it's important conceptually. So we model the probability of S equals 1, and I'm only showing you this among some S equals 1 people. And then we invert that to get weights. And then now we have these weights, and we can apply them. And so we're going to print out, let's see, this is the full data set of 100,000 people. That is the mean effect in all of those people, about negative 5.6%. This is the effect in the 2,000 people uncorrected, right? Negative 9.2%. That's the sampling bias that's been introduced by this weird sampling procedure. And this is after we apply the inverse probability of sampling weights. It is much, it's, like putting aside issues of precision here, this is much more like the negative 5.6 or whatever percent than that negative 9.2% is. So we have successfully cranked it back, right? Weighted it back to represent the thing in the entire population, give or take.
So what's the way to deal with precision here? I don't think I talked about that.
It's a mess. It's a mess is basically the answer. Yeah, but also just, bootstrapping is the answer, but it's actually completely unresolved as a question right now whether you need to, at least I think it is, whether you need to bootstrap the study sample only and treat the target population as fixed, or bootstrap both. And I think that there's some implications for what your study question is there, but I don't, let's talk about it. That paper has not been published, or that series of papers has not been published that I know of. The other thing to keep in mind about precision is that inverse probability weights are wildly inefficient. And the G formula is a much better idea if you care about precision and can make it work. Anything else to add there? Okay. So quickly then, that's inverse probability of selection weights. We can do the same thing using regression analysis, where if we fit these models with regression, it's, if you're not used to reading fast, it's the A effect. Again, negative 5.6% or so is the effect in the whole 100,000 people. Uncorrected, it's negative 8.6% in the 2,000 people, and corrected with these weights, it's negative 6.1%. So much closer to the truth in the 100,000 by applying these weights. And so this is just using the weights to adjust regression instead of adjusting a means procedure. But it comes down to all the same questions and the same answers, essentially. Now the inverse odds of sampling weights. What we do here first is that we imagine that we don't actually have the full 100,000 people. What we have is a sample of 2,000 of those 100,000 people, which is a little bit like the situation you just described. You don't have the entire state of California. You have a sample of the state of California, and you don't know who's, And this is exactly the same thing. Conceptually, our 2,000 selected people are in here, but not actually, not all of them are. And in fact, so as expected, in that sample, that random sample of 2,000 people, our estimated causal effect, it's a little off. It's not quite the negative 5.6% we thought it was before. It's negative 4.4%. Let's see. But and it's still biased in the same way in the sample, right? It's negative 9.2%. And now we can't model the probability of S equals 1 in this random sample from our target population, because in particular there's only 37 of those 2,000 selected people happen to show up in this sample of 2,000 people, right? So we can't do this directly. We got to concatenate now. And so we concatenate the target and the sample, and then we calculate, I'm going to highlight it, we calculate the probabilities, and then we calculate both the inverse probability of sampling weights and the inverse odds of sampling weights. And for the reasons that I showed you over on the board, the again, this is in the full data set, that negative 4.4%, negative 9.2% in the 2,000 people unadjusted. When we apply inverse probability weights, we adjust somewhat but not entirely back to negative 7.2%. But when we apply the inverse odds weights, we go all the way back to negative 5.1%, which is much closer than the odds case. Right? So there's the probability weights not getting the job entirely done because they're not quite right under these circumstances, but the inverse odds weights do work. Right? Or